Hello everyone, we are the senior project team with Woodward. Our project is a laser weld cell. So Woodward is an aerospace company, and right now they use EV welding for a lot of their welding operations. But one of the issues that they're having is they're having a difficult time getting like a high first pass yield because of the weld quality. So one thing that Woodward wanted our senior project team to do was design a laser weld cell that could do the same welding operation, but to see if laser welding would give a better result compared to EV welding. So some of the major specifications for this project all involve pretty much like the vacuum chamber. So one was that the vacuum chamber had to be able to be pumped down to 10 to the negative 2. Another one involved the rotary. We had to select a rotary that could vary between 0 and 100 RPMs with a tolerance of 0.1 RPMs. We also needed to be able to move the wobble head plus or minus 1.5 inches based on the center in the X direction and 4 inches in the Z direction. So this is the design that we came up with. This uses an IPG photonics laser wobble head, and then the laser generators in the back there. And then this whole system is used to move the laser head to align it with the part. And this is the vacuum chamber, and currently in the aerospace industry, they're required to weld all their parts in vacuum pressure. So this is how the operator would use our laser weld cell. If they have a part that they want to weld, they would open the vacuum chamber, insert the part into the 3-jaw chuck, close the vacuum chamber, and then they would use the camera that's mounted on the wobble head to align the wobble head with the weld seam of the part. And that can be adjusted with this turn screw and this turn screw. So this one moves the wobble head in the Z direction, and this one moves it in the X direction. But so once that's aligned, then you would select your program on the HMI, and that would turn on the vacuum pump. It would pump down the vacuum chamber. It would turn on the rotary, which would spin the part, and then it would energize the wobble head. And then once everything's up and running, the laser beam is going to actually weld the seam of the part. Once that's completed, the program will tell the rotary to stop spinning. It will de-energize the wobble head, and the vacuum pump will stop operating. At that time, you can close the shut-off valve and then open the vent valve on the side of the vacuum chamber, and then take your part out, and it should be all welded.
This is the vacuum chamber that we'll be using for the project. It's a 10 by 10 inside chamber, and it's 10 inches deep. The rotary comes in the side here and is mounted with this plate that has a O-ring groove with an O-ring to seal against this face. Up here, this plate right here has an O-ring groove right on the bottom surface that connects to the plate and will seal off. And then the same thing with the back. That gives us a complete vacuum seal while allowing us to put this glass in here for the laser.
So this is the top plate that goes on top of the vacuum chamber, and we milled out a slot in the top so that a piece of fused silica glass can set in place right there. And then we're in the process of making hold down clamps that will clamp down on the piece of fused silica glass and keep it tight against the O-ring seal. The purpose of this is to allow a pass-through into the vacuum chamber, but still maintaining the vacuum pressure. So the laser from the IPG photonics wobble head will go through the fused silica glass and then into the vacuum chamber where it will weld the part. A part that's currently not here yet, but that's on order and will be here pretty soon or in the next few weeks, is a rubberized bellows. And the one that we ordered is a rectangular shape, and it will mount to the wobble head itself and then to the bottom of the top plate. And that will completely cover the fused silica glass, and that will be used to keep out any light contamination from the the laser and also to prevent the operator from getting blinded from the laser. So this is how we control the linear motion of the wobble head. We have a Z component right here and an X component right here. And we use these turn screws to advance the wobble head in both directions. And you'll use the camera to determine like the exact location of like where you need the laser based on the focal point and based on where the weld seam is in the X direction.
So here we have an IPG Photonics D50 wobble head. It's the entire unit right here. It runs a clockwise, counterclockwise, linear, figure 8, and an infinity motion type laser beam on the weld joint. So here we have the 1.2 megapixel camera that IPG is supplied with the wobble head. It actually has the crosshairs, so we're able to line up the focal point on the rotary arm that we need to weld. So here we have the fiber optic cable support. We actually made this in-house. It was made out of sheet metal, and it will actually give us the flexibility, whereas if we move the carriage system, it will not, or it'll still allow us to move it without any problems, but it's still rigid enough where it'll support the weight of the fiber optic cable. And pretty much the only specifications it needed is that the fiber optic cable must have a 0.1 meter bend radius, and obviously we're well beyond that. This here is the IPG Photonics chiller. Its main purpose is to cool the laser generator and the wobble head from overheating. It uses deionized water, and it also maintains the fluid inside it between 21 and 25 degrees Celsius. The pressure that it supplies it with is 1.5 to 3 bar, and it supplies up to 10 liters of water per minute, so it's a pretty good cooling system.
So this is the vacuum pump that we're using for this project, and that is connected to the back of the vacuum chamber. And we have a valve right here to open and close that. So we'll leave it open when we're pumping down the vacuum. And when we want to release pressure in the vacuum, we'll close this and then open a vent on the back side of the vacuum chamber. And that will restore atmospheric pressure to the vacuum chamber. So this is the table that we built for the laser weld cell. It's made out of 2-inch 80/20 aluminum extrusion. And then we have some tabletops. We have the main table, and that supports the vacuum chamber, the PC and monitor, the transformer, some other components. And then we have this first shelf that holds the laser generator. And then the bottom shelf holds the vacuum pump.
Alright, so a little bit about our power distribution. Separately, we're going to have our chiller, which is going to have its own 483 phase line. Other than that, we're going to have a separate 240 volt line coming through here. As you can see through the cabinet, we're going to have our main fusing, which leads to our first power distribution block. This 240 is going to lead both to our single phase transformer as well as our laser generator. Laser generator has internal fusing, so nothing in regards to the cabinet. Right here is a single phase 10 kilowatt single transformer. Like I said, we're going to have our 240 coming into it, and then outputting will be our secondary power is going to be 120. That is then going to come through our second distribution block. From there, once we have our 120, we can power our 24 volt power supply and pretty much power any component in regards to our system. So as I mentioned before, we have our main fusing and our two separate power distribution blocks. From here, from the transformer, we're going to have our 120. That's going to lead both to our secondary circuit breakers. It's going to lead to our PLC power supply, our main 24 volt power supply, and externally we're going to have a servo drive that's going to be running off 120. Our vacuum pump, which here's our motor starter, going to be running off of 120, and one separate safety relay, which is going to be running off of 120. Like I said, we have some extra fusing for each of these components. We have this 30 amp fuse block. This is gonna hold our Slovo fuse for our vacuum pump. Here's our terminal blocks. Currently we don't have everything coming up, but as you can see, we have our main lines, our I/O, and our interlocks coming from our laser generator and wobble head module. We also have a separate cable coming from our HMI that has to do with the main e-stop and the cycle start and power, of course, to this internal box. We will then have cables from our contacts in regards to our safety door sensor and our vacuum sensor. So all that's coming in to these main terminal blocks and secondary terminal blocks. We have a ground plane, of course, for anything that will require some sort of ground connection. Our main earth ground connection, essentially grounding pretty much our control cabinet, and then all of our separate 24 volt neutral and 24 volt hot. And basically this is going to regards to all of our inputs and outputs going to and from the cabinet. Labeling will need to be done eventually in regards to reducing confusion, but essentially that's the main control cabinet. Other than the last part to this, we have our LAN switch, connect all the components on one local network, 2 separate safety relays, all going to monitor our e-stop. So we have a main e-stop on the laser generator, our main system e-stop as well on the laser generator has interlocks as a secondary safety component, which will be monitored. And then the second one, since it's running off of a 120 volt, this will only be monitoring the safety door switch, but both of them are tied in regards to one system. So if one goes down, essentially safety is broken and will require a reset from the cycle start. On remark to the controls cabinet, a little added note, here's our motor starter. Still uncertain whether or not we can control the control coils of this motor contactor and from a PLC output. So if for some reason we wouldn't be able to, we do have an isolation relay to basically be controlled from a 24 volt output to then send our 120 volt hotline through the motor contactor to the vacuum pump. Here is our rotary servo drive. From here we have motor feedback, safe torque, and basically all of our power lines in regards that will then be leading back to our rotary on the side of our vacuum chamber. And then something that just came in today is this 50-pin adapter for all the I/O in regards to the actual servo drive itself. All right, so 2 main components of our system. One, of course, is going to be our HMI, kind of the interaction between the PLC for our system and the operator. And then we have our main desktop, basically to run all the web pages and the camera software in regards to seeing a live image. In regards to the desktop, we're going to have 3 Ethernet connections. Camera itself is power over Ethernet. And then for both our wobble head module and our laser generator, each have its own separate web page, which once you set your IP configuration, you'll be able to access it. That will show pretty much all your diagnostics in regards to each device, as well as in the case for the wobble head module, you can set up all your internal jobs that will then communicate with our wobble head and basically the style of wobble and just basically the overall general configuration for each job. As far as our HMI net, as you can see, it's not necessarily powered up, but essentially the way the program is going to work, we're going to have basically mainly 2 displays. We're going to have a main top bar that will have all your diagnostics coming from, like your analog signals coming to and from your wobble head module, your laser head generator. You're going to have basically just what we displayed it as is what you would normally see on a web page in regards to diagnostics. Like the circle dots as, let's say, your emission is on, what your power level's at. Pretty much what you would see on one of these web pages, you would more likely see on your main page of your HMI. You will then have one main screen, which you will go to select your job. So as you go to that, one requirement or basically thing they wanted was to be able to, based on a part number, be able to choose what joint they wanted to basically do, and that will then decide what job you actually run when you actually start the cycle. So from here, it's gonna this page will have like a numerical input that will say, hey, this is the part number we're running. From there, it'll pull up all the possible joints for that particular part, and then from there you'll want to confirm it, and then you'll be able to cycle start once the job is sent to the wobble head module. At that point, also on the PLC program side, we'll have some sort of data structure that contains all the part numbers, all the joints for those specific part numbers, and basically just be able to display what when based on what the operator chooses. So, and then of course you have your main e-stop and then your cycle start / reset for the system. So here we have a plunger style safety limit switch. As you can see, these wires are going to end up going through back to our control cabinet. We have 2 sets of normally closed contacts, which will be basically monitored from one of our safety relays. We don't necessarily have it right now, but we'll have some sort of attachment that will be either welded or clamped on here that will basically be able to determine whether or not this door has been closed or not. This will be used in both our, like I said, the safety relay as well as in the program to determine, hey, it's good to actually start welding, whether it's inspecting the camera or actually activating our laser generator. All right, so as you can see here, here's our single axis rotary. We will eventually need 2 connections that are going to be leading back to our servo driver in the controls cabinet. They are currently being shipped to us, but one is your UVW lines, just basically from the servo drive to ensure that mechanical rotation and the clockwise rotation is working properly. And then you also have your motor feedback, which will then also head back to your servo drive. That's all your diagnostics and simple stuff that you can refer in your program when you're configuring the servo drive itself. Alrighty, so here's the back of our laser generator. Here you have, as we described earlier, here's your optical output going back to our wobble head. You have your 2 lines in and out going to and from our water chiller. So here, Ethernet connection. This will then lead back to your desktop, kind of what I was describing earlier. It'll be able to set up and configure your web page to see all the diagnostics in regards to the laser generator. Here you have your 7-pin connection. This is your secondary safety watch. This holds both your 2 separate contacts for the interlocks of the safety generator. Here you have your 25-pin connection. This holds all your I/O, all your diagnostics, inputs, outputs, analog outputs, analog inputs. The only difference is this second line is all referred to as the remote key switch on the front, that basically determine whether you are in remote or local mode. And then you have your top 4 pins, and that's the e-stop on the front of there, which then will lead back to one of our safety relays. You have on the right here, you have your 2 internal fusing as well as your power lines. This is a 240 single phase power, so you have your 2 lines and then ground, which will then lead back from our controls cabinet. Alright, one of our last components here is our wobble head module. As far as diagnostics of just the component itself, you have your main reset as well as 3 little light indicators. More or less, you'll see more of your diagnostics on your main web page or either on the HMI. From here, you have your welding head connection. This is basically leading back to your wobble head. This controls from your job setup and how you configure each job. It'll have your X, Y, and Z directions. In regards to I/O, you have this 25D sub cable, which is leading back to the controls cabinet. Pretty straightforward. It's all your diagnostics in regards to inputs, outputs from your wobble head. You have your main power, which is just going to be a simple 24-volt connection. And once again, we're going to utilize our Ethernet port, which is leading back to our desktop to configure and view and open that web page.
So due to COVID, we've definitely ran into some issues. Almost all of the components have been delayed in some way, between not having enough time for machining in the machine shop or delays with several components from different suppliers. But all in all, I feel like our team has still been able to complete this project to a good endpoint, and we've been talking with Woodward, and they seem to be happy with the progress that we've been making.